The next example we will introduce under Carnot cycle is vapor power system, which is a control volume, and it's different from last time when we had an engine because that was a closed system. How does a vapor power system work? First of all, we have a boiler. Inside a boiler, you burn a fuel to generate a lot of heat. And then we have a pipe going through this boiler. Inlet we call number 4, outlet we call number 1. And at number 4, it's usually saturated liquid water, point F. Cold water goes in at number 4, and then it will gain heat released from combustion. It will heat up, so what comes out of the boiler is usually saturated water vapor, G point. This very hot steam then will further go down to a steam turbine. This is a steam turbine. What happens in a steam turbine is you have many different blades on a shaft. This is the shaft. Hot steam goes into this turbine and then it's gonna hit the blades, which means the blades will be made to turn. What comes out of the steam turbine is cooled down steam. 122 cools down. Where does the heat go? The heat is converted into the rotation of the blades. What is rotation? Rotation is one format of work. We call it WT, work generated by the turbine. The turbine generates work, so this WT must be positive. And then what we will do is to further cool down the hot steam number 2 by sending it to a condenser. Hot steam goes into this condenser and further cool down. What happens is it's going to lose more heat, QC, and we call exit number 3. Before we send it back to the boiler, we need to have number 3 go through a pump in order to pump up the pressure. And then we send it back to the boiler, 3 to 4. How do you make a pump work? You have to provide the pump with electricity. So electricity, which is work, goes into the pump. We call it WP, which is the work consumed by the pump. So now you've noticed to make this cycle work, the steam turbine will generate mechanical work, which later on you will convert it to electricity. However, at the same time, the pump will consume some work, which is WP. So what is the total amount of electricity this power cycle can generate? We call it W cycle. This is the net amount of work you can generate out of this thermal power plant. What is it? It should be WT minus WP. WT is the work generated from the turbine. WP is the work consumed by the pump, and the difference between them is the net amount of work you can generate as electricity. Next, we will sketch this process on a P versus nu diagram. And unlike before, this time we do have to involve the vapor dome because there's phase change. Let's recall on the P versus nu diagram, we have two constant pressure lines. How do you sketch a constant pressure line? You curve down, go straight, and then curve down more. Let's have two of them. One for T hot, the other one for T cold. Where's T hot? T hot is the temperature inside the boiler. And what is TC? TC is the temperature of the environment to which you release QC. You lose heat to the environment. So TC is the environment temperature. And just like before, the top one should be TH and the bottom one should be TC because TH is higher. Okay, let's start from 4 to 1. If you take a look, 421 is at constant temperature TH, so 421 must be on TH line. And then we know point 4 is F point and point 1 is G point. So 421 is pretty straightforward. This must be point 4 and this must be point 1. On TH line, point 4 is F, point 1 is G. This is F point and this is G point. Okay, and now let's continue. 122. How do we sketch 122? What happens in 122? 122 is an expansion process. What is the name of 122? If you forgot, let's go back. The name of 122 is right here. Process 122 is called adiabatic expansion. Adiabatic expansion. So what's going to happen to pressure first? Because it is expansion, pressure must become smaller, so go down. Next one, it's an expansion process, so x-coordinate, specific volume must become bigger, so to the right. So 122 must go down and to the right. Go down and to the right. It's a curve, slightly curved. Okay, 122, slightly curved. And then 223. What is 223? 223 is the condenser. That's where you lose heat. And this process is at constant temperature Tc. So 223 must be on Tc line. And next, what is the direction? If you forget, we can always go back to the name of process 223. 223 is called isothermal compression. This is a compression process. So the x-coordinate, which is specific volume, again, becomes smaller, meaning 223 must go to the left. 223, go to the left because volume becomes smaller. And then it's a constant temperature process at Tc. And then 324, finally 324. What is the name of 324? Let's go back. 324 is called adiabatic compression. Adiabatic compression. Because it's a compression, the y-coordinate pressure must become bigger. So 324 must go up. And next one, because it is compression also, the specific volume nu, which is the x-coordinate, must become smaller. So 324 must go to the left and up. So we connect 324. Go up and to the left. And again, just like before, what does the area of the enclosure tell you? Area of the enclosure tells you the same thing, just like before. Area of the enclosure is equal to W cycle per unit mass on a P versus nu diagram. The good thing is, again, we can visualize W cycle per unit mass. However, the downside is we cannot actually calculate the value because this is in irregular shape. And again, if you have a power plant, we want to know what the efficiency is. Efficiency again is eta and is defined purpose over cost. Purpose again is W cycle, the net amount of electricity you can output. The cost is QH. You burn the gas, you release QH. QH is the cost. And then just like before, W cycle can be rewritten to QH minus QC and then divided by QH. It is 1 minus QC over QH. Okay, just in case you forgot, from energy balance equation, total energy going in, QH, must be balanced by total energy leaving. Leaving, we have two. First one is QC, second one is W cycle. So from here, we can rewrite W cycle into QH minus QC. Okay, and then next one again, eta max. What is the maximum efficiency? Same as before, change Q to T. So it's 1 minus Tc over Th. Th is the temperature in the boiler. Tc is the ambient temperature. And we know eta must be always less than or equal to eta max. And equal sign is true if the process is reversible.